LDS. So basically, low density spreading, just to understand very clearly, I have added a clear explanation here. We already know distributed sequence CDMA, DS CDMA from old days of 11A, B, and B, A and G, right? It's pretty spectrum. And so what we do in that one is we take its data bit and translate into chips, and those chips go on the time on the same frequency, basically, but the chips are on time. In time slot 1, you will say 1, then time slot 2 will say 0, 1, 0, right? Another user will do on the same frequency with a different code their chips. So that is what DSCDMA is. Basically, it is in time domain. So there is a variation of this called multi-carrier CDMA, in which we just do the opposite. You have a code like 1 goes to 1010, but each of these chips go on a different subcarrier. Okay? And so multiple users will use the same time slot. They will have different code, and so each subcarrier will have a mixture of all these. Okay? So you can see the duality. Everything that you could do in the time domain, now you're doing in the frequency domain. This is called multi-carrier CDMA. And multi-carrier, so this one was extended by LDS to say two things. First of all, they said, now these are orthogonal codes. Both of these in the MC CDMA and DS CDMA, they are orthogonal codes. So when you take 4 bits permutation, I mean, basically the combination of 4 out of 4, there's some number, not all of them are orthogonal. Okay? So very small number of codes you get, that means very small number of users, and it takes time to select the code. So they said, why can we find out some way so that we don't have to worry about the code, we can just randomly get the code. Alright, so that is LDS. In LDS, they said, okay, we'll take a large number of subcarriers and then randomly select a code. Very little chance that 2 of us will select the same code. And so that is, and basically most of the code will be 0 anyway. So that will be very, that's why I call it sparse, because the number of ones is very sparse. Okay? If you do that, if 30 of us, select a code, and suppose the length is 60, the chances of it colliding is much less. And so now we don't have to worry about assigning the code before you can talk. You can just select a code and start talking. Okay? That is LDS. Low density spreading, and code can even be randomly chosen. Input and output are multi-bit symbols. And so basically, I have given you an example of a single bit to multiple bits. Actually, this is a simplification, because the input is not 1 bit, right? And the output is not a single sequence. Input is generally a complex number, right? And the output is even more complex. Okay? So when you do, if you see in the books, if you go and read about it, you'll find a lot of all this complex numbers, this and that. But this is the simplest way to understand it. Is that we have multiple carriers, large number of subcarriers, but most of them have zeros. Means we don't transmit on them. Right? But we transmit on some small number of subcarriers, and chances of collisions are small, and even if they're not orthogonal, we make it. Is that clear? LDS? Okay. So SCMA is a variation of LDS. Okay? It is sparse, multiple axes, and the main difference is that here you see, if I am going to send x minus iy, x plus iy, let's say this code, 01 code, I'm going to put that on all the subcarriers, same code, right? And which there is 1. So somebody came up with the idea, can we do better? do we have to repeat the same code on all the subcarriers, or can be just like, that, what was the symbol coding? Time, space, coding, right? And frequency coding, right? Similar to that, they came up with, why don't we just do some more better coding than just repeat the same quantity, right? And that is what SCMA is. That they don't repeat the same thing, they do something better. So, instead of repeating the same symbols on different subcarriers, as in LDS, optimally coded symbols are placed on the different subcarriers. So this is now they're trying to merge the idea of space frequency coding to LDS. Okay? Symbols are mapped to higher dimensional complex symbols and then mapped to subcarriers. Now this is little bit complex to explain, but basically they go from 2 dimension to 4 dimension and then you come back to 2 dimension. Okay? And that is just, very difficult to explain simply unless I go into multi-dimensional things. But the good thing is that the codes are non-orthogonal. And so you don't have to select orthogonal codes. Okay, so you have the full space. And more code books, and therefore you can have more users and more code books. By the way, each user, when they have one bit, they just need to know one entry, that one is this one and 0 is opposite of that. But if you have 2 bits, then you need 4 entries. If you have 3 bits, you need 8 entries, right? So that becomes a code book. Right? So here, you can have more code book, basically more codes, and sparse means lot of zeros in the code book, and all codes in one code book have zeros in the same location. This is a simplification they made. Now, LDS doesn't say that when you select a code, then its row number 15, 17, and 20 should be 0. Okay? In this the rule they made that each user, when they select a code book, make sure that the same rows are 0 in all throughout their code book, not everybody else's code book. So you don't have to ask somebody else where you have put zeros. But in your code book, all the rows will have the same rows will have zeros, as you will notice in the next slide. Okay? And this is basically how many combinations are possible. And then this kind of coding is good because you don't need permission to speak. As long as you use your code assigned to you, you can speak at the same time, and somebody else can speak at the same time, and somebody else can speak at the same time, and the base station will understand the difference. Right? Otherwise, you have to do this map. And here we will do the map still, but we can do a group map now. Right? A group of stations can speak at the same time, and most of them may not want to speak. All right? So that is SCMA. Now, SCMA, so example shown here, we are going to do 4 entries. So 4 C2, 2 of them will be 0. So there are only 6 possible code books. And we will use all 6. The only rule they have made is that 2 of the rows in your code book should be 0. Right? So 4C2 gives you 6. And so you have 6 users. First user is assigned code book 1. Actually, this has to be coordinated because 2 users cannot have the same code book, unlike LDS. So the base station will give you the code book, right? And when designing the code book, it will make sure that in the first user, 2 rows are all zeros. In the second user, 2 rows are all zeros. Third user, fourth user. They are different 2 rows. Okay? All right? So 2-bit symbols before requires k equal to 4, n equal to 2, and so that is 6 code books. 6 user can be supported over 4 subcarriers. Okay? And each code book has 2 zeros in the same rows, and then you combine the spreading and decoding. So now basically, another way to look at this is that normally what we do in LDS is that we take this bit as is coming in, make a QAM out of it. Remember that complex number? We take 2 bits and make a complex number, and then we do the spreading. Here, there are not two things here. It's just basically you take the bits coming in and you make 4 subcarriers out of them. Okay? So this is just one box. That's all it is saying. A question now. Okay. So the 4 users, what we are, these numbers 1, 1, 1, 0, 1, 1 are indicating is that this user wants to transmit 1, 1. This happens to want to transmit 1, 1. This user wants to transmit 1, 0. This user wants to transmit 1, 0. You take your own number. These are just randomly selected that the user wants to select, transmit. So now if this wants to transmit 1, 1, it will go to the 1, 1 column here and transmit that. Okay? Row, and this one will go to that row and so on and so forth. So these are just different 2 bits that they want to transmit. Because this code transmits 2 bits and 4 subcarriers. Yeah.
How does the number of subcarriers factor into this?
Yeah, so the thing is, more subcarriers you have, the sparser it becomes and less collision there is possibility, right? The dense coding like here, it is really not sparse that much. It is just 2 out of 4, and we are using all 6 possible codes. It is just more collision possibility, which means that if everybody started speaking, there will be more bit errors. Hopefully, not everybody will speak at the same time, and so there won't be a problem.
How do we get 4 as the minimum number of subcarriers? Or is that the minimum?
No, this is just design. So basically, the core, this network designer or network implementer selected that, okay, in my network I have so many users and I have so many subcarriers, so I'm going to use this kind of coding, right? So this 2 out of 4 is just design value, an example value, example. It's not that everybody has to have 4 subcarriers. Next door might use some less number of subcarriers. Yeah. Okay. So since there are 2 bits, we need 4 combinations. Okay. I'm sorry, the codes are by the column, not by the rows. So 0, 0 is the first column. 0, 1, 1, 0, 1, 1. Okay. When I want to transmit 0, 0, when this user 1 wants to transmit 0, 0, they will send this symbol on the first carrier and then nothing on the 3 carriers. Okay. When this wants to transmit 1, 1, it will take the last column, and then whatever is written in that column, it will transmit that on those subcarriers. Okay. This one will take what column now? Okay. So basically, as written in this arrow, it says the 3rd column. So basically, 3rd column is 1, 0. All right. 2nd column is 0, 1. Yeah. 1st column is 0, 0. So that's correct. 3rd column. This is 3rd column. This is 1st column. This is 2nd column, and this is the last column. No. Okay. Distinguish. No. They don't know what is coming in. So they don't know the column. But what they do know is who the user is. So they have the code book for user. So the receiver for user 6 will have the same code book open because it knows that the packet is coming from user 6. Okay, so we know the source, so we know the code book.
So the code book is constant.
For user 6. Right? Each user has a code book. Each user has a code. It's like this. When I speak to him, I speak in Arabic. When I speak to him, I speak in Chinese. It's a different code. So I know that I'm talking to him, so I'm going to speak in Chinese and listen in Chinese. That's my code. Yeah.
Columns, those are the
symbols. Those are simply the symbols. The vertical columns, 1 per symbol. 2-bit symbols here. 2-bit symbols. And the rows are the subcarriers. And therefore the code as well. The thing is, this is the code book, right? So what the user the receiver will do is, will take this code book and tries to correlate with all 4 columns. And the best match will happen with 1, 1. and then it will know that the probability of 1, 1 is 90%, probability of 1, 0 is 80%, probability of 0, 0 is 10%. Right? These are probabilistic. And then it will take the highest value. Okay? SCMA. So the last one is interleave division multiple access. Now, in this case, all they do is that they take the symbol and they take an interleave pattern. Okay? So generally, let's take an example of DS-CDMA. DS-CDMA is what? Anybody remember what is DS for? Direct sequence, not this way. Direct sequence, right? Direct sequence CDMA, in that we take the data symbols and we interleave them first. Did I put distributed? Yeah, remove it. So basically, interleave it. So what we do is we take the bits and we then mix them around. And then we go to the spreader. Then we change every bit to chip. Right? In IDMA, we take the symbols, spread them around first, and then we interleave them. And you don't have to spread them. Spreading is optional. So you can just take the bits as they are and interleave them. If everybody interleaves separate differently, and I know your interleave pattern, I can figure out what you sent. All right? So that's the whole thing, is that this gives you even more bits possible, because your spreading sequence does not have to be very big. You could just be 1 bit for 1 chip, or 1 chip for 1 bit, rather than 11 chips for 1 bit, like we use in 11. Right? So what you do is you take the bits and interleave it. So we are taking, let's say interleave pattern is 2, 4, 3, 1. What that means is I take the second symbol first, then the fourth symbol, then the third symbol, and then the 1 symbol from the first symbol. Now in this simple example, every symbol is 1 digit. So I will take the second one, which means 1, then 3, 2, 0. Right? Then I will take the next 4 symbols, and I will take 6, 5, 2, 4, 3, 1. So 2 is 5, 2, 4 is 8. Do it yourself, man. 5 and 7. You can figure it out what I mean, right? Take the second symbol out of the 4, then take the fourth one, then take the third one, and take the 1. Huh? Now this is the code. 2, 4, 3, 1 is the code that the user has selected. Okay, that's the code. That pattern is specific to the user. Oh, what does a spreader takes 1 bit and makes multiple chips out of it. A spreader spreads in time or frequency, whatever. So this is already spreaded up. So whatever this is inside this box. What is coming out? Interleaver simply takes the chips. So these are actually the chips, if you want to call them. No, see, in this case it is not optional. In DS-CDMA, direct sequence CDMA, if you don't have a spreader, you can't do anything. Everybody will collide. IDMA is optional. Okay? So far, the techniques that we have talked about, they were mostly related to modulation, multiplexing, things like that, right? Then I took out the 9 techniques, which are really not modulation. These are somehow given the same hertz. How can we make better use of the same hertz? The same band, right? Then we'll talk about how to get more band. But and suppose you don't get any more band, can we still do better than 4G? So these are 9 techniques. And we'll go through them one by one, except the last one I will not go through. Higher order modulation simply means that we'll use COM64 or COM256. That's, straightforward, you understand that, right? So other than that, what is 3D beamforming? So basically, most of the transmission right now is in 2D. Basically, when you have a vertical antenna, all the energy goes in the horizontal plane. Okay? And that is how they make the amplification. So basically what happens is, if you have an antenna which is omnidirectional, it will be sending something into the sky, something to the ground, and something this and that. And a directional antenna will compress it down to horizontal. Okay? So what happens is, more of the energy goes into the people and not to the sky. Now, if people live in the high rise and they live in the sky, then what do we do? All right? Then we need 3D beamforming. Right? So, some people living on the second floor, third floor, fourth floor, they can be covered. And people living on the ground can be covered as well. All right? And this is basically a special case of full dimension MIMO. Now, 3D is not the end. You could have a lot more antennas and a lot more control over things, and so that is basically, if you have large number of antennas, if you have infinite antennas, then it is massive MIMO, and then full dimension MIMO is the same name, and 3D is basically same name for the 3D beamforming, same name as 3D MIMO or full dimension MIMO. Okay, do you agree? Okay, right. She wrote a paper on the whole thing, so the whole paper 15 pages. Okay. All right. So everybody understands 3D MIMO now, right? So now we have to worry about the UFR exactly, not just in horizontal direction. Because if they're living in third floor, they won't get the signal before. Third way we can get more hertz, more hertz is that if I have two spectrums, one is designed for FDD and one designed for TDD. Okay, I got some FDD from 2G and I got some TDD from 4G. Can I combine them? So far you cannot. Now you can. So actually it turns out some of this has already happened in 3GPP, release 13 and 14. So what is happening is release 16 will be 5G. Release 11 or 10 was 4G. So after that 4G, whatever is happening is 4.xg slowly will become 5G. Okay, so we are already in release 13 is out, release 14 is being designed, and 15 and 16, that's it. 16 is 5G. All right, so this is something that they have already thought about, and that is that you have this FDD which is given to you as a pair. Pair means this can go up, this can come down. Right? And TDD, which is bidirectional, time division duplexing, you use half time this one and half time that one. So in either case, you use only half of the spectrum. In this case, when you're talking up, you're not using down spectrum. In this case, when you're talking up, you're not using the down direction. Right? So they said, why can't we use both directions? Actually, sorry, I'm a bit ahead of myself. So they said, why can't we combine these two? Bidirectional is coming in a minute. So, but the thing is, so now what you can do is you can take this up and talk at the same time. You can get 20 plus 20, 40 megahertz. 20 of the FDD, 20 of the TDD. Similarly, in the down direction, you can take 20 of this and 20 of that, or whatever, right? So this is combining of FDD and TDD spectrum is what is called FDD-TDD carrier integration. And right now there are only 5 carriers that can be combined, but the plan is to allow up to 32 carriers. No, these are not sub-carriers. There are 32 carriers, means 32 bands. Right? 20 megahertz is one band, one carrier. All right, is this clear? So the next thing is distributed antenna system. Also, this has happened. Basically, if you live in a high rise, Then how do you get the signal? 3D MIMO is one of them. Another one is to put the antenna in your building. So you can put one antenna in every floor. If there's a big antenna on the top, from there you run a cable to every antenna on the floor. So regardless of which floor you live in, you are covered. This is called distributed antenna system. Now this one is one antenna, one cable. If you have multiple antennas, you need multiple cables. Right? And sometimes the RF signal is converted to digital. Now what you bring down is also another choice you have. You can just bring down the RF signal as it is and broadcast, or you can convert into digital and do something. So yeah.
What is it working now?
Currently?
Yeah.
So if you go back to, I'm not going to say about 4G, but suppose you go back to 3G or something, if you live on the high floor, you are in trouble. It's just like if you live in the suburb, you are in trouble. Right? And so this is basically trying to cover everybody. Now this is the next one which I was talking about, this simultaneous transmission and reception, also known as full duplex. Right now we do only half duplex. FDD is half duplex, TDD is half duplex. Alright, he is thinking why FDD is half duplex. Okay, alright, TDD is full duplex, but you are using two roads for two directions, and so basically what it is that you could get on both roads two-way traffic. That's what we want, really. I mean, if there's a name for it. So right now, on the down direction, we cannot do up. On the up direction, we cannot do down. Can we do both up and down on both directions? All right? And so the answer is yes. This is the latest stuff. This is not, basically the thing is, now once these guys discover it, then it will come to 11, it will come to everywhere else in the world, right? But this is 2016 stuff. Actually, this is 2010 stuff. But, so the idea is why they don't do it? Because there are several problems. There are many, many issues. First of all, your own signal will interfere with yourself. If I'm speaking and I'm trying to listen, very difficult. Right? And everybody in this room, they started speaking and listening, then it is impossible, right? So the thing is, because my own signal is going into my brain and processing and everything else, and so the ears have lower priority. But since I know my signal, I can subtract it out, all right, and do, basically processing of the received signal also. But there are other problems, but anyway, so the thing is, because the transmitted signal is too strong, and second thing is there is a large gap between the transmit and receive frequencies. So here, if I'm transmitting, I will have to put my RF. I don't know where to put my RF because this is RF chain is occupied for that, and this is a different frequency, different filters, different things required, right? So that is another one. And in TDD, time is okay. Solid. Solution is self-interference cancellation. It can be done in the analog or digital domain and digital domain. Basically, is that you know what you're talking, subtract that out. So actually, when you use a full duplex speakerphone, that's exactly what you do. Is that when you speak, you don't listen to yourself. Basically, the speaker cancels it out. Yeah. The same thing as PDMA. Now, okay, so it is different concept than PDMA. PDMA was pattern division multiple access, where every user subtracts out other user signal, not their own. Right? So the nth user has to subtract out 1, 2, 3, 4 to get to itself. Right? And one doesn't have to subtract out anything, it is done. It gets the signal and it has the highest power, it's done. So PDMA is subtracting out other people's signal. Here you have to subtract your own signal. right? And then the problem is also that if two UEs are talking, and we are talking in this direction full duplex, this is talking full duplex in this direction, there is interference of all kinds at the same frequency at the same time. So it's not trivial. And the reason we didn't do so far is because the cost is high. So if somebody comes up with a cheaper method of doing this thing, then it will happen. All right? People have started thinking about it. The paper is 2010. Since it has not been implemented so far, it means, it will happen someday, but people are just still trying to simplify the chips, simplify the IC circuits. Okay? But you can see, things that we never thought before are now seen that people are thinking about. Dynamic TDD. Dynamic TDD has to do with that in TDD, you speak for some time, download, and then you upload for a short time. And the idea was that most people don't upload anyway, so we can do more download, right? But the problem was when they started implementing TDD, they realized that you cannot do it. You really have to have a fixed time. If I decide that I want to do half-half, C has to do half-half, he has to do half-half, he has to all the basis systems have to do same ratio. Okay, and the same time actually, not just ratio. When I'm doing down, everybody's doing down. When I'm doing up, everybody's doing up. Because if I'm doing down and you are doing up, your car or your mobile user will not be able to be heard because my transmission is so high powered that the mobile users are being drowned. Right? So every transmission, when there are neighboring cells, they have to do the transmission and reception exactly at the same time. So what 3GPP has done is given 4 combinations possible, 7 combinations, 1, 2, 3, 0 to 6. And they decide that, okay, all right, in this area in St. Louis, they're going to use 0. All the basis stations will use 0, which means that they will do D, S, U, U, D, S, U, U. D is down, U is up, S is switching from D to U. You need time to switch. For any cell. Okay? So everybody decides that in this area we are going to use this pattern. There are 7 patterns allowed. Different patterns have different D's and U's, and so there's different ratios. But you cannot use 8 simply because it is very impossible to just convey myself to tell you that what I am using. Otherwise, I have to tell you the whole vector, and then you have to use the same vector. So we just decided we are all going to use 3. Done. Okay. How this is not dynamic. This is static. Static means this will remain there for the next year. Right? So we are not going to change it. So now the question is, why don't we be dynamic? We need to change with the time, change with the demand, change with whatever reason we need to change the ratio. So all this is basically, is that dynamic TDD is that now they have defined a new combination in which you have D, S, U, S, and S, D, S, S. So S is flexible. Okay? So I can put a D here or U there. If I put D and U, then I have to put a S somewhere. And so it is flexible, so now I have to really send a vector to you. If I want to change something, I have to change it, set a vector. Okay? And you can change every 10 milliseconds, which means every superframe. And then we will have to, because there will be interference, so we will have to have some enhanced interference mitigation and traffic adaptation. Basically what that means is that we will have to change the pattern, and then the mobile will be asked to change it. And traffic adaptation simply means that depending upon the upload and download, we will change the U's and D's. Okay? And this will be further. So this is already there in one of these releases, 13, 14. And this will be further enhanced for 5G. This flexible frame is there. Not in 4G, in 13 and 14, right? So we are way beyond 4G now, in at least 3GPP. Yeah. S/D. Either it could be switch or it could be D. Because if it is D, then you can have two Ds right there. D, D. You don't have to switch. But this will become F. F becomes what, so that we have to make a switch here. What is F is? If F is D, then we don't have to switch. Right? If F is U, it is switch. Yes, any other question? Yeah. This can be? If, as I was saying, there are two stages here. First stage is maybe release 11, 12, I forget which release, in which you have to select one of the 7. Then there is one release in which you just declare one of the 7s. I mean, you can change so often, right? And then there is one release in which now this F is introduced where you can more than 7. You are not limited to 7. Okay? So this is a matter of releases as to when more flexibility is coming in. Yeah.
How often they change the password?
They can change every 10 milliseconds as said here.
I mean, like, because it takes too long to make all the numbers aware that you are changing the password.
Yeah, so the question is, it takes too long. Too long is actually very short. Now, as you saw, the things are going into millisecond range. And so the message to go from one end of St. Louis to another end of St. Louis probably is few microseconds, speed of light. And so, yes. So basically, it's 10 milliseconds is a super frame, right?
So all the neighbors should be aware that you are changing the password.
And they have to agree to it, right? I mean, if suppose I have too much traffic which is going downlink and you have too much traffic which is going uplink, we not agree. You say, no, hold on, I will get into trouble if I just change mine, right? So there has to be some agreement. And I think this is dynamic TV probably not going to happen that often, but it is allowed every 10 milliseconds. So what will happen is when I want to change, I will tell everybody and they will say, yeah, all right, if we all agree, then we change. Then license-assisted access is that basically it's also called unlicensed access. So there is so much of unlicensed means, actually I want to call it license-exempt band, like 5.8 gigahertz, 2.4 gigahertz. Why don't we grab that and use it for LTE? Right? Not for Wi-Fi. Use the Wi-Fi band for LTE. All right, so this is a different way of integrating. Basically, get all the unlicensed stuff. Obviously, if you take unlicensed stuff, you're not guaranteed somebody else may start their transmitter and you're gone. Right? It is not guaranteed to you. So this will be used mostly for complementary band. If I have two bands, I have this tiny band which I have bought and this big band which I haven't bought, I will combine them. Most of the time people will get good service, and when the complementary band is not available, you get some service. And this will be particularly used in public hotspots and in buildings. And there are rules in different countries. In some countries, some of these 5 gigahertz bands are used for radar and things like that. And so this is basically difference between this and the Wi-Fi thing is that in this case end-to-end LTE. The mobile knows all the signals that they're getting in the millisecond frames and things like that. In the case of Wi-Fi, basically get connected to some machine which translates the two protocols. Right? Here there's no translation, LTE to LTE. Everything is LTE. Right? And these are the bands. And there are different rules in different countries, different bands, but that is LTE-U, also known as LAA. Multimode base stations. So now, base station, mobiles are already multimode. My phone does 2G, 3G, 4G, Wi-Fi, doesn't do WiMAX, but does Bluetooth. But the base stations don't. They don't do Wi-Fi for sure. They do 2G, 3G maybe, but they don't do Wi-Fi. They're saying, why not? Let's do everything. Okay, whatever is best, they'll do it. Okay, so the main process is what you do how do you process all these different bands? Something is running at 5 gigahertz, something is running at 700 megahertz. So then it is important to understand this one. Okay, so just listen carefully. Basically, what they do is when they have something coming in, they pass it through, they amplify it first, they receive signal, then they do A to D conversion, and then they do intermediate frequency processing. So this is very high frequency. They bring it down to some frequency where we can process it. And that is called IF, intermediate frequency. And then they bring it down to the real frequency band, that 20 megahertz means they become 0 to 20 megahertz. And then we do the baseband processing. Okay? So we have very high frequency, which is 3 gigahertz or 5 gigahertz or something. Right? 20 megahertz over there. We bring it down to intermediate frequency, bring it down to the earth so you can look at it, and then bring it down further to 20 megahertz. Baseband. So I'm just trying to understand two words, IF and baseband. And so you need software-defined radios. So these are called SDRs because what they do is they use DSPs, digital signal processing. Okay, these are generally what you call FPGAs or the field programmable gate arrays, and they can sample the signal at a very high speed and then figure out what frequency it is. You know, normally we know the frequency, so we put the filter and we do all the processing depending on the frequency. In this case, we don't know the frequency, so and right this second I'm processing this band, next second I'm processing this band, next second I'm processing that band. Who knows that? This is a multi-mode, right? And therefore, we have to process all the bands. So we do all of that in the software. In the hardware, we do a sampling at a very high frequency. Okay. So SDR, so two terms. SDR, PA is the power amplifier. LNA is the low noise amplifier. DAC is the digital to analog converter. A3C is the analog digital conversion. IF is intermediate frequency, and B is broadband. Baseband. Okay. Now the reason this is important to understand is because this leads us to the second thing which will come up later. Yeah, go ahead. Okay, so we know the frequency. I'm sorry. I should say, if I am passing Wi-Fi, I know that I'm going to get 5.8 gigahertz. Except that what I'm saying is, I may have to switch to 2.4 gigahertz in a second because I'm talking to B station. And I may have to switch to 900 because I'm talking to 3G station or something. Right? So we know the frequency, but it could be any frequency. Huh? Critical warning. Stop recording. All right, yeah. So oscillator is also, no, please, let's see. Okay. So the point is that all of this here thing, in the radio, the analog parts are very expensive. They consume the most money and most power as well, okay, and the most problem. So D to A converter, A to D converter, and these two amplifiers, they are the expensive part of it. Now, if he is saying that this circulator is expensive part of it, oscillator, this one, yeah. So basically, I didn't explain the oscillator. What it is this oscillator produces a signal so that basically subtracts out the frequency. So this one, so if you want to bring it down from there to here, you take the difference frequency and inject that in, so the frequency comes down. And even that is expensive. So the analog parts we want to do minimum. So now we go back to intelligent multi-mode RAS selection. Now, if you are going to speak everything, then we have to decide which one to speak at what time. Right? So if you just dumbly select which is what is run right now, in your Windows, then it selects between wireless and wired It just selects because the speed of one is higher than the other. Okay, but it doesn't know that the higher speed network is loaded. Right? So intelligent means you have to know the load, you have to know other things, cost, and everything else. Based upon that, there will be a policy, there will be an algorithm which will let you decide whether it is 2G, 3G, 4G, 5G, Wi-Fi, Bluetooth, whatnot. RAT, what is RAT? Radio access technology. Okay. Hyperdense small cells. Now, cells will become smaller. Obviously, those only three ways to increase the throughput: spectrum, spectral efficiency, and the cell. So we are going to get cells are going to be smaller and smaller and smaller, and they are going to become denser. Denser means density. How many cells in a kilometer, right? Hyperdense. And so that would be called HESNET, heterogeneous and small cell network. Previously we had heterogeneous because there were one or two small cells. Now everything is small. And self-organizing, so we need all those things that we talked about. It has to be self-organizing because they might be in somebody's building, somebody's mall, and so on and so forth. And they might be going through DSL in the backward direction, in the backhaul direction, by home wireless. Mobility management. Now, if they go from my cell to your cell to that cell, you have to have all that mobility management. There's a lot of work to be done there. Forward handover, you have to hand over, right? And load balancing, and forward handover simply means that we do it in advance. So when I know that the user is moving from here to there, tell the other cell in advance, look, he's coming, and here is the keyword, password, certificate, everything for this guy. So get in. So that is forward handover. Load balancing between small cells and macro cells and multi-rat management and everything else. The thing is, these cells might be privately managed, privately owned as well. Mall may own them. Hospital may own them. So on. Yeah. This is slide what? New efficient. Intelligent, multi-mode. Okay, I forgot to put it here. Okay, I'll write 10. Maybe actually 11. All right. So the next one is, yeah. Ping pong. Okay. Ping pong is when a user is standing between two cells equally distant, then it cannot decide which one to connect to. They will try this one and then say, oh, no, that is better, than try that one and then try this one. And that is called ping pong, table tennis. All right. So now there are four techniques for energy savings. I got to go a little faster, sorry. First is that do not transmit. All right, when you are not doing anything, you have nothing better to do, sleep. Don't waste your energy. Then there is antenna muting. This is again very clear. Basically, you don't have to use 8x8 MIMO all the time. When the traffic is low, just turn off the 7 antennas and just do one by one, right? And cell on-off switching. In the night, if nobody is walking around, just turn off the whole thing, right? And so the question is, if somebody did turn off, what happens? So every few seconds you wake up and say, oh, I'm here. And so they know that you are there, right? But most of the time you are sleeping. This base station is sleeping. Right now they don't. But with this one they will do. Now what are the techniques to reduce the dollar sign? Right? CapEx and OpEx. Capital expenditure and the operational expenditure. Right? So SDN, NFV, NEC, and CRAN. SDN basically is software-defined networking. How many people know here software-defined networking? Okay, so those of you who are not raising their hands are not listening. Do you know software-defined networking? Have you heard of this word? Basically, what it means is three things. First of all, that you don't worry about this exact hardware because you just use a standard standard programmability thing, right? So you can program anything remotely. That's how it means really. program anything remotely. So you have to have 1,000 routers. You just can send a command and all 1,000 will understand that now you need to shut off. Now you want to shut off, change the parameter, whatever, right? And centralized control, because you're going to do it from the central one place. And so that will be used in the 5G. All right? And the main savings is that orchestration. You can do thousands of base stations, thousands of light cells, small cells from one command. Right now you need a lot of operators to operate each cell. With software-defined networking, you don't have to worry about it. Network function virtualization. Now, NFV is a concept where they're saying, why don't we use the cloud for everything? Why do we have to have this expensive hardware? Right now, if you go to a data center from a carrier, they have $1 million machines. Some do remote RNC, which is remote network controller, and some do IMS, NME. We have all these names, mobility management. And these are all specialized hardware and very expensive. You're saying, just forget all this, put it in a virtual machine and put it in a cloud, like Amazon, our own cloud. And it will be very cheap, and you can create as many as you want. So that is called network function virtualization. All these functions will be in the cloud. Then the third concept is MEC, mobile edge computing, is that every user needs computing to be done, and cell phones in particular. So why don't we bring it to them rather than everybody going to the cloud, which is far away? So they will put a cloud on every tower. Yeah. Yeah. So the fog computing really says that computing everywhere. So it doesn't talk about the cloud as such. Okay. Fog computing means that my cell phone, your cell phone, their cell phone, refrigerator, everything is doing computing. That is fog computing. And cloud computing is obviously opposite of fog, right? I mean, fog is on the ground, the cloud is in the sky. So the cloud computing means that you have an organized set of machines which are being shared by different people. That is cloud computing. And this is mobile edge computing. So basically, this is the clouds have been put on the tower for people to share. So you can have, strictly speaking, you don't have to have fog computing. You can do MEC. And if you have fog computing, MEC will work with that too. So this is MEC, is that putting the cloud on the tower. Finally, CRAN, Cloud Radio Access Network. So they said if they are going to put everything in the cloud, why don't we and centralize it, SDN, NFV? Why don't we do that to apply that to the radio network? So basically, right now, the antenna is on the top. On every antenna base, there is a small hut where they keep the baseband unit. Remember that baseband unit we talked about? Intermediate frequency and the baseband, etc. All that logic is kept in that hut. Right? And if you have 1,000 towers, you have 1,000 huts. In case of small cells, there is a small box. It does that. Right? So they said, why don't we just take all of those DBUs and move them into a central place in a cloud? So these things are called remote radio head, which is the antenna, which obviously you cannot put into a central place. The antennas have to be distributed, but everything else you take it to the cloud. Right? So this is called Cloud RAN, Cloud Radio Access Network, CRAN. And the main problem is that this is very high frequency signal, which you are taking from the antenna and taking it to DBU. Right? So generally you need 10 gigabits per second, either just a fiber optic line or Ethernet or something. Okay? And so you take all those bits over there and then process it over there. All right, now that we have saved the money, now the question is, can we get some more spectrum? The answer is yes. Most of the spectrum, new spectrum is not available in the current range, like up to 6 gigahertz, everything is very tightly filled. But they have made a list. They have made a list to the government. Every government, please give me this 3.4 gigahertz, 2.3 gigahertz, this and that. So they will get, a little bit here and there. All right? But most of it is going to come from 6 to 100 gigahertz. All right? That is where there is a lot of spectrum. But the problem is that 6 to 100 gigahertz, actually, so there are, you can see here, if you are going to do small cells, these are good because they don't go too far anyway, and they have large bandwidth, right? If you do the medium cells, you can do 60, something like that here. Macro is still where it was supposed to be. And then IoT doesn't like any of this. IoT needs distance. That means it likes lower frequencies. It likes 700, 400, like that. So the IoT will stay, very low frequency. Okay? And so these will be free, 6 to 100, right? And they will be complementary, and they will be used whenever you can use them, but there will be always little bit required here, which is license. So above 6 gigahertz, and there is a whole ITU study which talks about why above 600 what happens. And so the main problem, we already know all this, so I think I'm going to just repeat it quickly because we have discussed this before. The loss increases very fast with the frequency. So it cannot go very far, like 100 meters it can go. And if you go from outdoor to indoor, the windows kill it. So you cannot go too much. Mobility, Doppler shift is also proportional. You cannot be running it, in the car. The channels are wide, which is good. The antennas are small, which is good. And so you can do up to 1 kilometer, 2 gigabits using millimeter base. We have already talked about all that. So now there are two more things to be done, and they have to do with the application specific. So what can we do and two key applications are video and Internet of Things. For Internet of Things, they call it machine type communication, MTC, versus human type communication. Currently when we do cell phone, that is human type communication, where at least one end is human. Machine type communication is both ends are human, machines, and therefore it is also called M2M, machine to machine. Right? And the cost has to be low, but anyway, you can use GSM, the old technology, which is cheap now, $5, and you can use even extended coverage with some simplification of the GSM. However, they want to do LTE. Right? We are going to close down GSM shops, so we want to do LTE. Right? So for LTE, they have M2M, D2D is cars, basically, to nearby cars. And then we have group communication, which is when they want to talk to each other, like in police or safety, then they take a radio and then they talk to them. There is group communication. And then, this is actually more video, so I'm going to skip that one. For MTC, what they have done is they have defined in LTE two new categories of users, of the user element. So this is a standard. Actually, this is also a standard, but this is low cost. So low cost user is called category 0. Previously, they had category 1 to 14. 14 was highest powered, lot of equipment. 1 was the oldest one, but now there is 0. 01 has only one antenna, cannot do any more than 1 megabit per second, does not have full duplex filter, and has a power saving mode added. So this is good for IoT. Right? Then they said, no, this is not good enough. So then they added category -1. This is not category -1, it is category -1. Okay? And this is called LTE-M, MTC LTE. Okay? Here what they said was that we don't have to have 20 megahertz, you can just do with 1.4 megahertz. So you can have even cheaper equipment. Okay, and 1.4 megahertz only allows you 6 symbols. Remember, each resource block. Each resource block was 12 carriers, 12 subcarriers, right? 12 by some number of symbols, 7, right? So you can have only stacked up 6 of them, and it gets you to 1.4 megahertz. And so now what happens is, because you have only few subcarriers, you can put more power and still not exhaust your battery. Otherwise, you have to listen to all the 20 megahertz. Now you don't listen to anything other than 1.4. You don't transmit anything more than 1.4 anyway. So that is called PSD boosting, power spectral density boosting, because you are putting power in some cases. And that gives you better thing. So this is called LTEM. And actually, and they also reduce the power to 20 dBm. With 20 dBm, the amplifier does not have to be separate. It is a very cheap amplifier which can be put on the chip. So now you can get, instead of $5, maybe $2. Well, this is not enough. So now they have third one called category -2. Okay, category -2 is called narrow band LTE, NB-LTE. Okay, in this case, instead of 6 PRB, they have just 1 PRB. And they just use 128 kilobits using 200 kilohertz. So not even 1.4 megahertz, cut it down to 200 megahertz. What is 200 megahertz? 200 megahertz is 1 GSM channel, if you remember from GSM time. Okay, so 1 GSM channel they take and they put LTE on it, and it is called narrow band LTE. So now you get 1 PRB, and so you have this for machine type communication. Now the problem is, okay, if you're not listening all the band, how do you know the whole map when the rest of the people are transmitting? So they have to define new signaling. Previously the signaling was spread all over 20 megahertz. Now instead of being vertical, it is horizontal. So they are going to give the signaling for 1.4 megahertz people, they will have this signaling here. For 1 PRB, they will have one of the subcarriers actually devoted to, because these are 12 subcarriers, some of the subcarriers devoted for the control. All right, so they have to make these changes to support narrow band. Okay. Power savings mode has been implemented, which is there in standard in actually Wi-Fi all the time, is that you can go to sleep and you can go short sleep first, and then you can go to long sleep if you don't have anything to do. And so these IoT devices will be mostly doing that. Now for the video. For the video, actually, they noticed that video is the most of the traffic anyway right now. So this is totally other end. Now we talk about IoT, which is the lower end, and we are talking the high end, which is video. For that, there's a new protocol called DASH, Dynamic Adaptive Streaming over HTTP. Now this is a competition to video over IP. So the IETF has worked out quite some complicated stuff for video over IP. You have to forget all of that. And all we need to do is go to the web server as they are. So no change to the web server, and tell them that please send me the second scene of this movie. Okay. So the scenes will be defined. So all they have done is they have designed a what they call MPD, Media Presentation Description. That document simply defines the whole movie. It says, okay, this movie has 1,500 scenes. Scene number 3 begins from here to there, and it is coded for this kind of TV. This is, so on so forth. All the information is MPD. So first you do is you go to the web server and say, give me the MPD. And then whatever user say usage, go forward, go backward, all of that the device can do by simply requesting proper bytes. So that's simple, basically. So that's what I call dash. And the dash is simply adding that MPD. No other thing. And obviously we'll do caching and other things. That brings us to the end of 5G, ahead of everybody else in the world, believe it or not. You know. Yeah, well done. So 7 things. First of all, 5G is defined in terms of 8 parameters. We saw that 8 octagonal diagram with circle, right? Then they have new techniques that give you more bits per hertz, and those are f-OFDM, FBMC, NOMA, and so on and so forth. Then they have new methods of getting more, squeeze more out of the spectrum, the same spectrum, without changing multiplexing. So there were lots of those. Then we had energy savings mechanisms, we had dollar saving mechanisms, and then we had specials for IoT and video. Right? All right, now